Hi, and one last time, welcome. Today is a very special day. Today is the day I'm making the last video of the series. Today's topic is Bayesian testing. We're going to start with the first basic question, which is why do we need tests? The answer is going to be fairly straightforward. We are going to very broadly define what tests are for. Then I'm going to introduce you to two frameworks. Because first I'm going to introduce you to the classical framework of testing. This is partly because the Bayesian framework, sometimes it feels like an extension almost of the classical, although it's completely different. But at least mathematically, you don't just have a parameter space, you have a Bayesian parameter space, which has more structure. So that's one reason. The other reason is that in these videos, I keep contrasting the classical and the Bayesian view. And I said from the start that I'm not really going to dive into, and I'm still not going to, into what the classical view is. Also, side note, I'm calling it the classical. Maybe people take offense with that. I'm not even sure if historically who came first, but it's just, I say classical because that's what I usually see in university being taught. At least that's the way you introduce to statistics, so that's why I say classical. So maybe that's not the best word for it. Usually people say frequentist framework, as a side note. The other reason, as I said, is that I want to contrast these two views, because these are two views you're going to be confronted with. That doesn't mean that they're exclusive, that doesn't mean that they are in combination. In fact, there are many, but it's good to know what the difference is. So this video, in some sense, is going to be a mirror of the video we saw at the very first part of this video series, but we can now expand on all of the definitions that we have, since we now know the mathematical background. Also, that being said, I'm going to use the very first example as well. The example about somebody doing a test for a disease, because I think it's a very nice example. It's very simple, and it's very good to introduce all of these new measures that we're going to be talking about. So first classical framework, then the Bayesian framework. This is the framework you should be fairly comfortable with, but I'm going to include now some way to think about testing in particular, because we did estimation theory, and testing for Bayes theory, it's basically estimation, but it's a little bit different. It feels a little bit, or it's a bit more specific than what you usually see, just because it's used so often. Then, after I introduce both of these, I'm going to exemplify the difference on the topic of two-sided testing, partly because this is a very interesting case for Bayesian statistics, because it's apparently contradictory, and partly because at this level, this is where the classical and the Bayesian ideas most differ, and also their results differ the most. And this is what's called Lindley's paradox. It's an example where it not only appears that the results are different, but also that they even seem to diverge for larger sample sizes. And that's pretty much it. I hope this will give you a good oversight. And then the question is, since this is going to be the last video, the question is going to be, what now? I finish with a quick recap, and I'm going to first talk about what you can do after this lecture, and also what I'm going to do with this YouTube channel. Okay, so let's start. Why do we need tests? Let's go back to our very first example. There is a disease. 1% of the population has the disease. One person is chosen randomly. Now we want to know, is this person sick? So this is how it starts. We have a statement. The statement, for example, could be, the person is not sick. And we want to make a decision. We want to decide, is this statement true or is it not true? The statement here, I phrased it in this particular way. It's going to be slightly different in the video. I phrased it in this particular way because this is sort of our baseline, and this is usually how people indicate the null hypothesis. I'm going to talk about how to choose the null hypothesis in a moment, but often, at least in medicine, the null hypothesis is what's usually the case. So here we have the usual case is going to be that the person is not sick. At least 1% of the population has the disease, so that makes sense. Really, what you do for classical testing, at least for Bayesian testing, it doesn't even matter. But for classical testing, the way you choose H0 is you say, what kind of error do I want to avoid? Again, there's two types of error. The type 1 error, and the probability of type 1 error is the one we want to control. We say H0 is false, but in fact it is true. This is the error that we want to avoid. This is why it's called type 1, type 2 error problem. Type 2 error is just the opposite. We say H0 is true, but it's false. We can only control one of these in classical testing. So that's also where phrasing comes in. We want to avoid type 1 error, and that's how we choose H0. Also, we can choose the alternative hypothesis, H1, which is just the opposite. In this case, the person is sick. So now all we need is to find out how we should test. In the classical framework, as I mentioned, we want to control type 1 and type 2 error. There's a very stringent way to do this, which you have to follow to the letter. If you miss one of these steps or you mix these steps up, that can have pretty unforeseen consequences. So we have a very conservative frame. But let me first introduce it. So how does this work? There's 5 steps you need to follow. First, we need a statistical model. So we need a sample space X. In our case, that's 0 and 1. If you remember the first video, 0 means not sick, 1, sorry, 0 means the test is negative. So in the example, we did an actual test, like a medical test, and the test was negative. If we saw 0 and positive if we saw 1, we need a sample, a parameter space, theta, indicating if we're not sick, which is 0, or if you're sick, which is 1. And we have to say, how does x given theta behave? We have two cases. If we're sick, then x given us being sick, so x given 1, is going to be very likely to be positive, so it's Bernoulli distributed with factor 95%. In the other case, if we're sick, it's also Bernoulli distributed, but with a factor of 5%, because then it's very unlikely to get a positive. That's what we had in the description of the exercise in the first video, again. So, after we have our statistical model, this is when we define the statement which we want to analyze. So we define H0. In our case, H0, the null hypothesis is that the person is not sick, so that theta is equal to 0. Generally, how we write this is that theta is in some subset of theta 0. In our case, that's just the set that contains 0. And okay, if we define H0, we also know H1, but we should also define it. We have H1, which is the statement that theta is in theta 1, in our case that we are actually sick. So this is the set containing 1. After we define this hypothesis, we have to choose, in the classical framework, we have to choose some alpha, which is a number between 0 and 1, for which we want to use alpha to control the type 1 error probability. You can control the type 1 error, which is the probability of declining, of saying H0 is false, even though H0 is true, by just very rarely declining. That's also why you increase the probability of type 2 error, which is the probability of accepting even though something is wrong. Okay, so we choose some alpha, and we want that alpha binds the probability of type 1 error. So this is the probability that our test, I'm going to define what a test is shortly, that our test says 0. So this mathematical test, this is why it gets a bit confusing, because unfortunately I designed it that way. In the first exercise, that 1 means that the test gives evidence against H0, but here we say if this is 0, we say we reject H0, and we don't want to do this when H0 is true. So we want to control this probability. And how do we do this? We have to design a test which is just a function from x to 0 and 1 for now at least, where we say phi of x equals 0 means we reject h0, phi of x equals 1, we accept h0. And then after we've done all of these 4 steps, then we can actually execute the test based on the data that we actually have, which is x. So this is the classical framework. You will notice there is no prior in any of this. We have no prior assumptions. And that is actually a good thing, because partly maybe you don't want to bring prior assumptions into a test, but also just if you have less stringent requirements, you can do more. If you don't have a prior, or if you don't know how to do a prior, you can still do this test. On the other hand, we're talking about type 1 and type 2 error. We're not talking about the kind of errors that we want to control, which we do in Bayesian statistics. In the Bayesian framework, we care about the probability that theta actually is in theta 0, so that H0 is true, given our data. And we've already learned how to deal with this. If you think about it, for a test we want phi of x, and this won't be the case because life isn't that nice, but we want that this is 1 if H0 is true, so if theta is in theta 0, and 0 if that's not the case. So we want theta, we want this to be equal to the indicator function of theta being in theta 0, which is just a fancy way of saying what I just said. In Bayesian statistics, this is an estimator for this function. And we already know how to estimate things. We know now what to do, because this was the third video. We need a loss, and there's several ways to do this. We can do this with the 0,1 loss, which says if phi of x is equal to this function, that's fine. 0 loss. Otherwise, the loss is 1. That makes sense. That's the naive approach. But we could also say, wait a second, there's 2 kinds of errors that we can do. For the test, as I mentioned, there's the error of saying, okay, you know what, I'm not sick, but you're actually sick. And then there's the error of saying, I'm sick, but in fact you're not sick. These kind of errors have very different consequences. For one error, you could say, you go to work sick, that's really bad because then you get sick and you work while you're sick, and that's very bad for your health, and then you get other people sick, that's very bad for their health, it's very bad for the company because then everybody gets sick and stays at home. And we could say, we give a weight to this consequence, which is A0. Actually, it's A1. And then A0 is the weight of the other consequence. The consequence of saying, I'm actually sick, but in fact I'm not. And that's also, you don't want that, because then you stay at home, even though you could have worked. So, with this loss, we have that it's defined as A0. If type 1 error happens, so if phi of x is equal to 0, even though if phi of x is equal to, if phi of x is equal to 0, even though h0 is true, so if theta is in theta 0, we say it's a1, so a1, like these are positive numbers, it's equal to a1. In the other case, where phi of x is equal to 1, even though the alternative hypothesis is true, and it's 0 if we actually don't mess up. Now, what do we want to control? We want to control the conditional expectation of the loss given our data. And we can calculate this for the A0, A1 loss, because there's only two mistakes that we can make. There's a probability that theta is in fact in theta 0, and given our data, we can reevaluate this probability. And if this happens, we pay a price if phi of x is equal to 0. Otherwise we don't. And the price is A0. The other possibility is that theta is in theta 1, in which case we pay the price of A1. So what's our decision? We have to choose between those two errors. We say phi of x is equal to 1 if and only if this error, A0, has this probability, it's larger or equal to the other error times its probability. And you can rephrase it, because actually this probability, it's equal to 1 minus the other probability. You can rephrase it in saying that the probability that theta is in theta 0 is larger or equal to A1 over A0 plus A1. So here we see that our decision does not only depend on the probability that we assign to these events, it also depends on the consequences, which I also think is very nice about Bayesian statistics. Of course, we saw all of that in the third video. Now, there's some summary measures, which I'm also going to introduce. First, the test itself for Bayesian statistics. Also, I should mention, I should go back. I didn't talk about this loss, but this is just the case that A0 is equal to A1. So we just care about the posterior probability. So phi of x is equal to 1 if and only if the posterior probability is larger or equal to 1/2. Which makes sense, right? We just look at the probabilities and that's all. So back to summary measures. In our test, we had, in the example, we had the posterior probability of H0 being true, so that's 1 minus the probability of us being sick, is 1 minus 16%, which is pretty large. It doesn't mean that the test itself is bad. Remember, for the test we had, the medical test, we had type 1 and type 2 error, so that's a very ideal situation. Smaller equal to 5%, actually exactly equal to 5%. So intuitively you would say the test itself is still a high quality test, it's still good. But there was prior evidence for rejecting the test anyway. Still, for any, we need to somehow say that the test is good, independent of the prior, kind of independent of the prior, because you can always find the prior, which has super low probability for H0, such that even the best test gives you a different result based on the prior. So one way to balance this is the Bayes factor. The Bayes factor measures how good the test is, kind of based on the test itself, and not really based on the prior. And the way it measures this is it compares our ratio of prior probabilities of H0 and H1 being true with our updated ratio of posterior probabilities. And this is very nice because it measures how good a test is. What's the implication of this? Well, imagine you make a study for other people to use. So you make some study and you want to find something out, but really the result of the study means nothing without your prior, if you want to make a decision. But you don't know the prior of the other people. So what you do is you publish the Bayes factor, and this is what is actually done. And then people can decide themselves what their decision is. And I think that's very nice. And it's really easily done for the simple case where theta, it can just take two values, let's say small theta 0 and small theta 1. Because then we have that this here, it's just equal to, okay, this probability is just pi in theta 0 by Bayes rule times the sampling distribution in theta 0 divided by pi in theta 1, which is in this case H1. So I should specify this is then the event of H0 being true. This is the event of H1 being true. Again times the sampling distribution just by Bayes rule. And then also the prior probability of H0 being true is just pi in theta 0 because we only have two values. And then we divide by pi of theta 1, and what happens is that these probabilities, the prior probabilities, they cancel out, and we're only left with the value of the sampling distribution in 2 points. So this value is independent of the prior, but that's only true in the simple case. In the not so simple cases, we still have to see how pi actually behaves on this area. I mean, if this area is just one number, we don't care, because there's only one number left. But in general, you have to integrate over the whole area. So there we still care about the prior. The prior doesn't just cancel out, but we can still see how good the test is based on how it changes our prior beliefs. That's the idea. Another idea is that instead of the 0-1 loss, we think about the squared loss. So we say, what is the difference between our test and the value it wants to estimate squared? So we think in terms of distance. Now we have a continuous measure of evidence. This is very similar to the p-value, if you know what a p-value is in classical statistics. We just want some number as close to our estimator as possible. You know, this is the squared loss, so we actually know how to calculate this. This is just the expectation of this indicator function given x. But that's just the posterior probability. And that's another way to think of the posterior probability. It's an estimator that should indicate how far we should believe H0. So this is all of the ideas we need for Bayesian statistics. Now let's go to one quick example of Bayesian statistics versus classical statistics. The example is the case of two-sided testing. What is two-sided testing? This is the case where H0 just says that theta is equal to some constant, theta 0, just somewhere in theta. And h1 says the opposite, that theta is not equal to this constant. So we test equality. Why is this so interesting? Well, for Bayesian statistics, you seem to have a paradox. Because if pi is continuous, which is what we usually do when we have like a large interval or something as our parameter space, then the probability that theta is in theta 0, it's just 0. Of course it is, because theta 0 only has one value. The probability to have exactly one value for a continuous distribution is 0. So this is a problem. And the question is, how do we deal with this if we have a continuous measure? The answer is we don't. We just take a different measure. We say pi of theta is equal to some constant rho 0 plus 1 minus rho 0 times some measure pi 1 of theta, which is the probability density on theta 1. And this here is just some constant in 0, 1. So this is a discrete continuous case. This is a mixed case where we say, okay, there's some probability for h0 to happen, and if it doesn't happen, then we have a continuous measure on theta 1. This is a bit weird. On one hand, pi should not depend on h0. After all, our prior probabilities are based on our prior beliefs. So we don't say, okay, I want to test this, and because I want to test it, this is my belief. No, I say, this is my belief, and then I want to test this. On the other hand, it makes sense. Why does it make sense? Well, we want to do the test. And if we want to do the test, that means that we think that it's definitely possible that this thing is h0, otherwise why bother testing? So there should be some small probability that h0 actually happens. And for this particular case, you can see we kind of have a bias for h0, because we have this very thick, not continuous but discrete density for h0, and then we have a continuous density for h1. And so what can happen is, and this is called Lindley's paradox, if we look at this line, and let's say 0 is theta 0, so this is our h0 being true, and this whole line, excluding this point, it's theta 1, and let's say we have some density, let's say the uniform, so we gave everything here the same probability, the same density, then if we have some estimator, let's say the maximum likelihood estimator, let's say the best value for f of x given theta, the best approximation is here, and let's say that is close to this best approximations, they have a very low prior. On the other hand, this value here still has the same prior. So if you just get very close to this value, if the best ratio that would fit our theta, it's very close to theta 0, but it's not exactly theta 0, then we would still choose h0, even though h1 fits much better. H1 has one value that fits much better. So even though this rainbow value is better, because it's so much more unlikely under h1. And then on classical statistics, you can have completely different results, which say, there's a much better fit, so we're going to reject h0. So this is a huge difference between classical statistics and Bayesian statistics. This is where they can differ. I show you the Wikipedia article, which gives you an actual example. And I also show you a study where they talk about how to choose priors for these two-sided cases or more general cases. One thing I want to note is that for Bayes factor, this is actually very nice. Because the Bayes factor, remember, it's the posterior probabilities, their ratio divided by the ratio of the prior probabilities. Because we have these kind of simple hypotheses, this one is just rho 0 times f of x given theta 0 by Bayes theorem. This here is 1 minus rho 0 times this integral over theta 1. And the priors are just rho 0 divided by 1 minus rho 0. So what happens is, again, rho 0, it factors out. So this is again one example where we have this Bayes factor and we don't even need to know our prior belief in H0 to determine the Bayes factor. So we can just give other people the Bayes factor and they can decide what to do with it. Yeah, this is just one example where they differ. I will send you some links if you want to read further into this. And this ends our video. So what now? If you want to continue reading, I recommend you, if you want a deeper knowledge, to read the textbook. It has been an absolutely amazing book. I can highly recommend it. A huge part of these videos is based on this textbook. In fact, I'm not even sure how long I will keep these up, just because I feel like I'm taking a bit too much material from the textbook. I will ask the publisher and ask if they're okay with this. But otherwise, maybe I will have to take these videos down eventually. And the second thing that you can do is use the knowledge that you have gained here. I hope that this course gave you a different overview, gave you a different view on on statistics in general. I hope you've gotten a better understanding. The point of this course was not to convince you that Bayesian statistics is better than classical statistics. It was first to point out the alternative, but also to point out, for me at least, a huge part that was missing in classical statistics. It does not mean that one is better than the other, because in classical statistics we have also many advantages. The huge advantage being that we do not have to choose a prior. And we've seen in the last lectures, choosing a prior is messy, it's difficult. There's many different theories, and I give you a link to a research paper that's been published, I think, last year. And they're still arguing about how to properly choose a prior, and even showing how different priors can give you so different results, even though they're supposed to model the same thing. So statistics is messy. That's the bottom line. Bayesian statistics is messy. Classical statistics is messy. If you mix both of them, it gets even messier. The good thing is your understanding of these topics. That's what matters, because I really liked this idea in Bayesian statistics of having some prior beliefs, because usually you have prior beliefs, and updating them. That's how you should think about tests, not as like some thing that you just have to accept, because the data, it doesn't mean anything without our interpretation of it. So this is the last video. I've skipped many topics, which you can see on the different numbers changing. You can read up on the different topics that I've missed in the textbook. I might someday again make videos to fill up these numbers, depending on how it goes. But for now, this series is over. I want to thank you so much for watching these videos, for your interest. I really hope that I could help you at least a little bit in understanding this very complicated and very interesting topic. I also want to thank my supervisor, Christian Debraband, for making this project possible. It has been amazing. So what am I going to do now? I'm going to continue making YouTube videos, but I want to try to make more high quality videos. I want to try to actually animate stuff, give more effort into this, get very different topics, very interesting topics, and that's why I'm going to continue making videos, but I'm going to take my time with them. The goal for now is, instead of one video a week, which I tried and failed at the end to do, I'm going to make one video a month. I hope, if you enjoyed these, that you keep watching, and I'll do my best to provide the best content. I'm dragging this out. It has been a great time. I hope this was useful, and yeah, I hope you had a great time as well. See you.